So I think we can continue now. So my pleasure to introduce Julia Knight. She's talking about the generalizing a question of Gromov, and there's a part 2 later on, like I think it's Thursday. Thank you, Julia.
Well, thank you very much for including me and for allowing me to speak remotely. So this is joint work with Johanna Franklin, who will speak on part 2, and also Turbo Ho. And Johanna and I are grateful for NSF support, which brought her to Notre Dame for a visit, and we started this project on that visit. So I'll give an outline of part 1. I'll first talk about an original question of Gromov. Was, what does a typical group look like? And he was thinking finitely presented groups. And there's a conjecture of mine, which is still unproved, on the elementary first order theory of the typical group. Then I'll talk about generalizing Gromov's question to varieties, algebraic varieties, in the sense of universal algebra, so equational classes. I'll say what this means. So we generalize the question, asking what's a typical structure in these other classes. And we'll give some examples illustrating different possible behaviors. And then in part 2, Johanna Franklin will talk about some general results suggested by the examples. Okay, so Gromov's question. What does the typical group look like? And Gromov described in terms of limiting density what it means for the typical group to have some property. His ideas, well, in the paper where he first asked this question, he introduced some important notions. That of hyperbolic group was introduced in this paper. And the notion of limiting density was not made quite precise, and he claimed that the typical group was hyperbolic, but that proof also was not quite precise. So Gromov's ideas have been made precise in different ways by different people. Olshansky and Kharlampovich and Miasnikov will mostly follow their approach. So to define limiting density, we have to say what are the presentations we're going to allow. So maybe I should say something about presentation. So some people now use the term presentation when they mean isomorphic copy, but I don't do that. I remember what is a group presentation, and I think in those terms. So, so for groups, a group presentation is a group presentation, not an isomorphic copy of a group. So we need to, so there are different possibilities for this limiting density, but we have to restrict the number of relators in some way. Without any restrictions, the group would almost surely be trivial. And this was proved in Olshansky's paper. But I remember long before, in 1982, there was a gathering at Carol Wood's cabin on Cape Cod, a bunch of logicians plus the group theorist David Benson. And it rained the whole weekend. So Benson had suggested a game, well, really several games, in which we would build words based on our initials or our birthdays, and then we would spend some time figuring out that the group we got was trivial. So we were sort of generating evidence for this, but it wasn't proved until Olshansky's paper much later. And in fact, David Benson didn't actually know a proof when I asked him a year or so ago. So limiting density in Olshansky's definition. So the allowable presentations have a fixed tuple of generators and a fixed number of relators. And for each S, PS is the number of presentations in which the relators have length at most S. So they could be shorter, they can vary, but the relators have length at most S. And PS of Q is the number of these presentations for which the resulting group has property Q. And the limiting density is the ratio of those two as S gets large. Now that might or might not exist, that limiting density. We'll mostly be talking about the property of satisfying some elementary first order sentence. And then we'll talk about the density of phi instead of the density of the property. So typical and free groups. So the typical group does have some properties in common with the free groups. By a result of Olshansky, the group is hyperbolic. So Gromov had claimed this and Olshansky gave a proof. And by a result of Kharlampovich and Miasnikov, any two bases are Nielsen equivalent. So that means that there's some finite sequence of very basic transformations of one basis to another. You can replace one basis element by its inverse, or reorder the basis elements, or the third elementary transformation is replace one basis element by the result of multiplying it by another basis element. So any automorphism of one basis to another can be gotten by applying a sequence of these transformations. Any new basis can be gotten, not any automorphism, but any new basis can be gotten by a finite sequence. And in fact, it's effective to tell what are the words that take one basis to another. And that was proved by Nielsen, that effectiveness. So I had asked Benjamin Fine, a group theorist, about some other property. Now I can't remember what it was, but he just said, in the sense of limiting density, all groups look free. And I thought about that and decided to try to make that precise, that comment, offhand comment. And so thinking about elementary first order theory of the free group and of the set of sentences you get with limiting density 1. So take presentations with at least 2 generators, a fixed number, but at least 2. So you're getting the non-Abelian free groups then. And take just one relator. So this was the Kharlampovich and Miasnikov version. And let Fn be the free group on n generators. For an elementary first order sentence phi, the limiting density always exists. And it has value 1 if the sentence is true in the free group and 0 otherwise. So it's maybe worth thinking about the following. For different n, the theory of the free group on n generators, n bigger than or equal to 2, is always the same. And this was a result of Sila, for which he won the Karp Prize, and also Kharlampovich and Miasnikov. So the theory of non-Abelian free groups is actually complete. Well, so for the conjecture, it's still open, but there's a little bit of evidence or experience that makes it plausible. So one thing, Paul Shoup, just in conversation, said it sounded plausible to him. And Kharlampovich and Sklinos have a paper available showing for a slightly different notion of density, not the one that we're using, but it's a version that has a parameter d, and the number of relators can actually vary, but it's bounded in terms of d and the length. So they show that for density d less than 1/16, and phi, a universal sentence, phi is true in the typical group, if and only if it's true in the non-Abelian free groups. So their paper is available on Math Archive and has been for a year. I think it's been revised some. And Coulon and Ho have a different approach, And their paper isn't yet available, but they're again showing, they're using the Olshansky definition. And they're showing that for universal sentences, the statement is true. So let me turn to algebraic varieties. A language is algebraic if it consists just of function symbols. And so this is not the sense of algebraic geometry, of course. For an algebraic language L, a class of structures is called an algebraic variety if it's axiomatized by sentences that start with a tuple of for all quantifiers and then in front of just an identity. And the definition, it's really that of an equational class, but it was a theorem of Gromov and Maltsev that this is equivalent to the original definition of algebraic variety in universal algebra. So presentations, so it's like group presentations. So let's fix a variety, and let's say T is the theory generated by the axioms. A presentation is a pair, a tuple of generators, as for groups, and then a tuple, not of relators, but of identities. So the relators are really telling you this word is equal to the identity element of the group. So this is the analog of that. It's saying what are some identities that we're saying are going to be true. And then Gromov and Maltsev separately developed this notion and showed that for any finite tuple A, there's a well-defined free structure with generators A, and that the identities that hold in that free structure are exactly the ones that you can prove from the axioms for the variety. And they also showed that each presentation, the tuple of generators with a finite set of identities, yields a well-defined structure, and I'll just put brackets around the presentation. And this is always a homomorphic image of the free structure. And it has the feature that the identities that are true in this structure about the generators are exactly the ones that are implied by the axioms for the variety, together with these identities from the presentation. So let's fix a variety and a set of allowable presentations. And when we try to show or determine whether it happens, show that the sentences with limiting density 1 match those in the free structure, this next lemma will simplify things a little bit. So it says it's enough to look first for some elementary invariants for the theory of the variety, theory T, and to show that we have a match for those sentences. So what this says is if we've managed to show that P and Q have density 0 or 1, then P has density 1 if and only if the negation has density 0. And P, I'm saying not P, I'm really thinking of P as a set of presentations, and not P is the complementary set of presentations. And this union that has density 1 if at least one of the two sets has density 1, and intersection has density 1 if both have density 1. But what's going to be important to us is these are sentences, P and Q are sentences. Okay, so let's turn to the first example. So it's what Johanna and I began doing was to try to think of the very simplest thing we could, simplest example, where we hoped we could actually calculate the limiting densities for all sentences. That was really our goal in thinking about this example. So the variety of bijective structures, it has a language with two unary function symbols, S and S inverse. And the axioms say that those unary functions are inverses of one another. They're total, one is the inverse of the other. And if we're thinking of structures with a single generator, say A, well, then what we get for these bijective structures with single generator, we either get a Z chain in which the successor goes forward and the inverse successor goes backwards. But yeah, so we have a chain, or else we get a cycle of some finite size. And those are the only possibilities. So A generates either a cycle, and S and S inverse are inverses. So we think, well, what does S do? It goes around this way. S inverse goes around that way. And all elements in these structures, all elements are automorphic. Any element could just as well serve as the generator. A looks like any other element. So we have a result for the bijective structures and presentations of the form. We have a single generator A and a single identity. So for simplicity, I've written it as if all the function symbols are on the left, but we get the same result if we allow function symbols on both sides. But anyway, let's think about presentations where the function symbols are just on the left. That's what the group theorists did. You know, they moved all the function symbols to the left. All the AA inverses such to the left. Anyway, so the sentences true in Z have density 1, and therefore the ones false in Z have density 0. And I'll outline the proof. I'd like you to see not details of the proof, but what's involved in showing this. So what we first did was find elementary invariants. And every sentence, every elementary first order sentence is equivalent in this variety to a finite Boolean combination of special sentences. I'll say what those are in just a minute. And then what we did was show that for the special sentences, the density is 1 if the special sentences is true in the free structure, and 0 otherwise. And then using that lemma, we're done. So let me say, what are the elementary invariants? So over the theory of bijective structures with any number of generators, every sentence is equivalent to a finite Boolean combination of sentences saying either for some n and k, there are at least k cycles of length n, or that for some n, there's a chain of length at least n, distinct elements of length at least n. And to show this, to prove this proposition, there are different methods we could use, but what any model theorist would do would be to look at saturated models. And once you decide to do that, it's very easy. So then the densities. So we want to show that the special sentences true in the free structure on a single generator. For our presentations with one generator, one identity. So we want to show that the sentences true in the free structure have density 1. And it's really enough to show that for the sentences saying that there's a cycle of size n. There's at least one cycle of size n. And we want to show that those have density 0. That's really going to be enough. In all the bijective structures, the sentence for the sentences saying that there are at least n at least k cycles of size n, those are just false for k bigger than 1. And the sentence saying that there's a chain of length n, that's true as long as you don't have an m cycle for m less than n. So the calculations are elementary here to show that. So for the limiting density for the special sentences that matter, well, so we look at the total number of presentations of identities of length at most s. And that's 2 to the s plus 1 minus 1. And then we show that the number of presentations in which there's an n cycle is 2d, where d is some sum of combinations. And this is not difficult to show. And then we apply Pascal's lemma, and we use an approximation for, we factor out some of the combinations, leaving a part that depends on k, and we approximate that part using Stirling's lemma, Stirling's formula. And then we managed to show that the limiting density is 0, as we should. But I was trying to say, what are the ingredients? So it's all elementary. You know, Pascal's lemma, everybody knows that. Stirling's formula, we all know. There's a little bit of counting that uses familiar things. Then second example is unary functions. So we'll consider the variety with a single unary function symbol f and no axioms. So that's the variety of unary functions. And we'll consider presentations with a fixed generator A and one identity. And this time we'll allow the function symbol to occur on both sides. So the identity has to have form, some number of occurrences of f on one side and some on the other. So that's it. And the results that we get say for unary functions, that variety and presentations of this form that we're thinking about, a single generator and a single identity, the sentence saying that f is not 1-to-1 has density 1, but it's false in the free structure. The free structure is the copy of z. The function is 1-to-1. Sorry, it's a copy of, I haven't said what this free structure is. It's going to be a copy of omega, though. We'll have f iterations of f on A. So the sentence saying that f is not 1-to-1, it turns out has density 1, but it's false in the free structure. And all sentences have limiting density 0 or 1. So I'll say a little bit what's involved. So first, the structures. So for a presentation of the form we're thinking about, single generator and a single identity, let m prime be the smaller of the two numbers, and let n prime be the difference. And if n prime is 0, if we're saying that fn of a equals fn of a, well, that doesn't tell us anything. And what we're going to get is just an omega chain. It's just the free structure. And if n prime is bigger than 0 and m prime is 0, the difference is 0, then what we'll get is an n cycle, n prime cycle. But if these numbers n prime and m prime are both bigger than 0, then what we'll get is a chain of length m prime followed by a cycle connected to a cycle of size n prime. And this sentence phi, if you think about it, when are we going to get a function that's not one-to-one? It only happens in case 2. Whoops, let's see, did I say? I think I said the wrong thing. So in the omega chain, we have one-to-one function. In the Z cycle, we have a one-to-one function. But when we have this non-trivial chain followed by a cycle, then we have not one-to-one. So I said the wrong thing here. Okay, so for arbitrary sentences, we can say what happens exactly also. And we say it in terms of a picture here. So there is a structure, not a finitely generated one, such that the sentences with density 1 are exactly the ones true in this structure. And what the structure looks like is a sort of limit of these finite chain followed by finite cycle, as the length of the finite chain and the length of the finite cycle both grow. So you can sort of look at the this chain and imagine that it has become infinite. So we see the beginning of it, and if we run around to the other end, we would see the end of it. But if it's become infinite, if m is infinite, we don't see the whole thing at once. And then for the cycle, if that's also become infinite, well, we see how it starts off, leaving this point where we witness the not one-to-one, and we see where it comes back, but it's made an infinite loop and we can't see the whole thing. So that's our structure to look at that tells us what sentences have density 1. The theory of this structure is decidable. In fact, the theory of all the structures that we get on one generator is decidable. You know, each one is decidable. But if we take various other infinitely generated structures, it's easy to produce things with different numbers of cycles of different sizes and get a non-decidable theory. So the third example, we'll look again at bijective structures, but this time we'll take 2 identities instead of 1. We'll still have just one generator. Our presentations will have 1 generator, but we'll have 2 identities instead of 1. And there's a sentence, an easy sentence to state, saying that there's a 1 cycle, or equivalently, if we're thinking about just 1 generated structures, the whole structure is a 1 cycle. So for these structures, so this sentence does not have limiting density. And we'll see, I'll indicate a little bit what's involved in showing that. So for identities equivalent, now I'm moving the function symbols to the left again. So if we had things equivalent, identities equivalent to SM of A equals A and SM prime of A equals A, where M and M prime are integers, we could even assume they're both non-negative. The resulting structure satisfies C, just in case the GCD of these 2 numbers is 1. So what this means is that there's no prime that divides both M and M prime. And what happens, why don't we get a limiting density? Why doesn't it exist? We sort of get 2 different limiting densities, one for the even S and a different one for the odd S. So what happens is that the limit as S goes to infinity of the number of presentations where the identities have a length at most 2s over the total, and the resulting structure satisfies C over the total number, that approaches one limit. And if we look at the 2s plus 1, the limit as s goes to infinity, so the odd bounds on the lengths, we get a different limit. The limits both exist, but they don't match. They're strictly in between 0 and 1. And I'll say more. I'd like to give you some idea really what's going on in this proof without giving the details. So let's consider presentations first just with one identity to see a little bit some of the ingredients. So consider just a single identity and let x be the difference function. So the difference between the number of occurrences of s and the number of occurrences of s inverse in that left-hand side of the identity. And for t of length 0, x takes only value 0, of course. For t of length 1, we can get value -1 or 1. You know, we've added, we didn't have any s's or s inverses, but now we add either an s or an s inverse, and then that difference has value either -1 or 1. And then for length 2, well, we add another s or an s inverse, and now we either have two s's or two s inverses or equal numbers. So the difference function takes values -1 or 0 or 2. And then for length 3, we can have values -3, -1, 1, or 3. For length 4, we could have values -4, -2, 0, 2, or 4. We can calculate the probabilities of these for the fixed lengths. But what's important to notice is that for odd length, you can't get the even values, and for even length, you can't get the odd values. So that says something important. So for t of even length, 2 is going to divide this difference function. And for t of odd length, 2 is not going to divide the difference function. And then using elementary methods, we could show, we can calculate what is the limiting density if we were only thinking about odd. Now there's some work to do here, but it's like what we did before, and we can do it. So the limit, for the identities of length at most 2s, both even and odd, the ones that have 2 dividing the difference function, the limiting density of those is 2/3. If we were just looking at even s, and if we were looking just at odd s, we would think the limiting density was 1/3. There's 2 dividing that difference function. The biggest length really dominates and makes a big difference, changes what we're getting. So the limit is toggling between 2 values. And that's going to happen when we're thinking of pairs of an x and an x prime also. So to deal with odd primes, though, let's think what would happen if we just had a single x and we were thinking about odd primes. Then to figure out what goes on, even just for a single identity, we have to use a result from random group theory. And it concerns a random walk on a finite cyclic group, say of length n, say of size n. And what the result says is that as k grows, the probability of, so we have a walk on the group. So we're at each step, we're moving from one group element to another. And certain ones are accessible in one step and certain ones take more than one step. So the result says that the probability of reaching various group elements after k steps is approximately uniform, and that the convergence is very, very good, exponential and uniform, even over choosing different groups. So we use this result several times. But one thing we can get from it just immediately is for any odd number n, for example, an odd prime like 3, and any s, the limit of I wrote this prime saying, well, we're thinking just about one identity, not the setting we're really interested in. So the limiting density would be approximately 1 over n. Would be 1 over n, the limiting density. So our presentations don't have just one identity. We're interested in presentations with 2 identities. And so let x and x prime be the difference functions that we get, corresponding to these strings of symbols on the left. And our presentations have, it's really an unordered set of identities. And the random variables, x and x prime that we get, these difference functions, they're not really independent. But the limiting densities, we can show, we're trying to show that certain limiting densities are 0. And if we manage to show it for the ordered pairs, we would also get it for the unordered ones. So what we're going to do is consider the unordered pairs and allow repetition. So we're considering different kind of presentations. And if we do that, then the x and x prime are really independent. So we use that. Another thing that we use, and I won't justify it, but it is justified by this many uses of this lemma from random group theory. So for distinct primes P and Q, the events P divide X and Q divide X, similarly the events P divide X prime and Q divide X prime, these are not independent. But in the limit, they behave as if they were independent. And this takes really several clever ideas from random group theory. And I won't explain them. But let me say then how the calculations would go. So I want to claim that this special sentence C that says there's a 1 cycle, that doesn't have limiting density, and it's because the limiting density toggles between 2 different values. But let me show you what those values are and how we arrive at them using the intuition of this independence. So let dp be the event that P divides both x and x prime, or the set of presentations that give the structures in which that happens, the bijective structures in which that happens. So for the prime 2, we get for even lengths, so P2S, 2 divides both x and x prime, divided by the number of presentations, this P2S, the total number of presentations of length that, where the identities have length at most 2s. So this limiting ratio that we'd be looking at, where the bound on the lengths of the identities is 2s. So we get a limiting density of 4/9. And what that comes from is the independence for x and x prime. We're taking the product of 2/9 by 2 ninths. So it's the product that 2 divides x, the limiting density of that, that's 2 ninths, and the limiting density 2 divides x prime. So that's where this is coming from. And then for the odd, so we knew that for a single identity, the limiting, we'd have an even limiting density of 2 ninths and then of 1 ninth, of 1/3, sorry, 1/3, and for the odd length, we would have a limiting density 1/3 for the 2 divides x, and similarly for the 2 divides x prime. We take the product because those really are independent, and we would actually get 1/9 now. So we know this first line, that's not relying on something, it's still elementary. So that's really telling us that the limiting density of 2 does not divide both x and x prime. I'm writing that as negation of D2, complement of D2. So that's going to toggle between the 1 minus 4 ninths, the 5 ninths, and the 8 ninths, that's the 1 minus 1 ninth. Okay, so for odd primes, p, 3 or 5 or so on, we actually get a limiting density. It exists. So the limiting density of dp, p prime p divides both x and x prime, is 1/p squared. And then the limiting density of p does not divide both x and x prime. So that has limiting density 1 minus 1/p squared. So this is based on, it's based on the independence of the x and x prime, and that result I'd stated earlier saying that for odd primes, p divides x, just for a single identity, has limiting density 1/p. So that's what's behind this. But that used the ideas from random group theory. Okay, so now we're going to state something that involves more and took some effort to prove, and I won't give the proof. So what we're interested in is p no prime divides both x and x prime. We want the limiting density of that, because that's when C holds, the sentence we're interested in. We get a 1 cycle, just in case no prime divides both x and x prime. Okay, so if we say no odd prime divides both, let's look at that one. And I could write that, just that statement, it's the conjunction over odd primes of x and x prime are not both divisible by p. And the limiting density for that exists, and it's equal to the product over the odd primes of the 1 minus 1/p squared. It's what you would think might happen if we really had independence of these different primes, divisibility by the infinite different primes. And we don't have that, but we get this statement just as if that happened. And this took some effort to prove. And then what we're really interested in, whoops, sorry. For C, the statement, no prime divides, 2 doesn't, and also the others don't divide both x and x prime. And what we're going to, if we assume independence, then what we would be doing is just taking the product of what we would get for limiting density 2 divides and some, well, 2 doesn't divide, and no odd prime divides. So that's this product. And for even S, we get the limit that's the product of C and this 5/9. We were toggling between 5/9 for not both divisible by 2. And then this 8/9, not both divisible for the odd, not both divisible by 2. Okay, so that's all I'll say about that proof. And I'll say just a little bit about the fourth example. So it's again groups, but Abelian groups. So it's a perfectly good variety. And we'll consider Abelian groups in presentations with a single generator and one relator, or an identity saying that that relator is equal to 0 in the group. And what turns out to happen is that some sentences do not have density, and others have density strictly between 0 and 1. So here's the idea. For P a prime and n bigger than or equal to 1, let beta of Pn say, so it's an elementary first order sentence saying there exists an X such that P to the n divides X and P to the n plus 1 does not divide X. And of course, we can say that in the language of groups. And for P equal to 2, so we have 2. There's some X such that 2 divides X, sorry. 2 to the n divides X, and 2 to the n plus 1 does not divide X. So that's what this beta of 2n is saying. And it fails to have density, again, because the even and odd limits don't match. And the calculations are a lot like the ones that we just did for the bijective structures with two identities. So I won't give the calculations, but they maybe look a little bit similar. There's a common part, and there's a factor that changes for even and odd. So we're getting different limits. They both exist. So the limiting density itself does not exist. It's toggling between the two different values. And then for odd primes P, beta of Pn has limiting density. And it has limiting density what you might expect. So if you think of what are the possible remainders after division by P to the n plus 1. So this density, it exists, but it's a value properly in between 0 and 1. So in the one case, for prime 2, the sentence doesn't have limiting density. For the odd primes, the limiting density exists, but it has value properly in between 0 and 1. So again, these calculations, these use that result from use the ideas from random group theory, much like the previous example. So this, my original conjecture on groups, I believed it when I conjectured it, when I stated the conjecture, but actually seeing this result makes me think I didn't have very good grounds for making that conjecture. This particular example, I didn't have very strong grounds. There was just some evidence that there were examples of properties of the free groups that seemed to have limiting density 1, but only a few known examples, and I was conjecturing on that basis, but I'll stop here.
One second.
Sit down. Can you hear me with my mask? Maybe I should.
Yes, I can hear.
In the beginning, you mentioned limiting the number of relators because if there's too many of them, then you just end up with the identity group.
Yeah.
And I was wondering if you let the number of relators grow sufficiently slowly, like relative to the size that the relator can be, like, is there a way to make it grow so slowly that that can be avoided? And if so, where does that occur? Or if not,
Well,
maybe something about why.
yes, in fact, so this result of Kharlampovich and Sklinos is exactly for that sort of notion of limiting density. So they have a parameter D, and the number of relators grows slowly, being bounded in terms of D and the length of the relator, the length of the relators. Yeah, so it's exactly what you're saying. And this was a notion of limiting density that Gromov had introduced it without making it quite precise. Olshansky did make it precise, and I think other people have made it precise. And that was the notion that seemed to Kharlampovich and Sklinos more natural to use. To be honest, I was using Kapovich and Shute because I had read their paper, and this was unfamiliar to me when I made the conjecture.
Cool,
But,
thank you.
Yeah.
Thank you. Any question? Let me check real quick the block. Okay. So thank you very much, Julia. We're going to have a half an hour coffee break, and we should be back at 4.